So this is the video corresponding to Chapter 4, Sections 4.1 through 4.5 of the text Basic Sentential Logic and Informal Fallacies, which is used in Philosophy 10 Introduction to Logic at UC San Diego. In this video, I'm going to talk about those sections, which is basically the introduction of replacement rules into the proof method. So in Chapter 3, we got an introduction to the proof method along with inference rules. Now and also conditional proof. In this chapter, we're going to discuss replacement rules, indirect proof, and proving tautologies. And we're going to start off with replacement rules. Now what I'm going to do first is just introduce the first three replacement rules, and then I'm going to discuss the differences between replacement rules and inference rules, because there are some key differences, which is why they're introduced in separate chapters and have different names. The first is conditional exchange, which we will abbreviate as CE. Now you can immediately see one difference, which is that we are representing the rules slightly differently. Instead of lines going from top to bottom arranged horizontally, here we're vertically. We're now arranging them horizontally. And we're separating the two parts with this quadruple dot, like a double colon. The way to read this is what conditional exchange says, is that if you have a conditional, you can swap that for a disjunction as long as you negate the first component. So we can turn if phi then psi into not phi. We've negated the first component, and then turn the horseshoe into a wedge. Conditional becomes a disjunction. Now, one reason that we are representing these horizontally rather than vertically is that these can go in both directions, and I'll demonstrate this in a minute. So not only can we use this rule to turn a conditional into a disjunction by negating the first component and changing the operator, we can also change a disjunction into a conditional. We can go from right to left. Same thing. We can turn the wedge into a horseshoe so long as we negate the first component. Not phi becomes phi. Okay, let's see the next rule. Double negation. This one is extremely intuitive. You can change phi into not phi and vice versa. Basically what this rule says is that you can add and subtract tildes as long as you do it in pairs. You can add 2 or subtract 2. You can't add 1 or subtract 1. Finally, the final of the first three we're going to introduce is commutation. And this works on both disjunctions and conjunctions. And what it basically says is that the order doesn't matter. So if you have phi or psi, you can change that into psi or phi. And ditto with the conjunction. Phi and psi, you can change that for psi and phi. Okay? Now, before we see some examples, I want to talk about some of the differences between inference rules and replacement rules. One difference, which we've already seen, is we're just going to represent them differently. Instead of a vertical sequence of lines, it's going to be a horizontal pair of lines, maybe more than one pair. As was the case with commutation, we had two versions, a version for disjunction, a version for conjunction, as you can see here. Some of the rules will have multiple versions like this. Another key difference is that the replacement rules can be used on parts of a line. The inference rules, recall, had to correspond to whole lines on a proof. The replacement rules can be used on part of a line. So here's an illustration. Suppose these are just 3 random lines from a proof. We'll just number them x, y, z. It doesn't matter what they are. Line x, I have a conditional whose consequent is itself a conditional. I could use conditional exchange on line x to turn this conditional here, it's part of a line, into a disjunction. Okay, so I have a conditional. I can turn the horseshoe into a wedge. I have to negate the first component. B becomes not B. The rest of the line stays the same because I only used the rule on this part. So I only changed that conditional. Now I can also use the replacement rules on entire lines. So for instance, I can move from line Y to Z. I can use conditional exchange on Y to change this conditional into a disjunction. Horseshoe becomes a wedge. I negate the first component. A becomes not A. Okay, so they can be used on parts of a line. They can also be used on a whole line. If you use it on part of a line, the rest of the line stays the same. Okay, so I used it just on this part. Everything else just falls down and just stays the same. Okay, you've only sort of manipulated this component of the line. Another difference is, so this is just illustrating the fact that I used it on part of a line here, or use it on a whole line as I did there, either way. Now, the second difference is that they can go in either direction. So the example I just gave, I'll just move back up here, I was turning conditionals into disjunctions. And so in 2 steps, I turned both of these horseshoes into wedges. You can go the other way. I can turn wedges into horseshoes, right? So I could, line X, Y, Z, X is a disjunction whose second disjunct is itself a disjunction. I can apply conditional exchange to X to turn this wedge into a horseshoe, this disjunction into a conditional. I have to negate the first component, not A becomes A. The rest of the line stays the same because I used the rule on this operator here. The rest of the line comes down exactly as it was. And if I want to change this into a conditional, I can. Wedge becomes horseshoe, negate the first component, the rest of the line stays the same. So they work in both directions. Okay, so those are the 3 main differences. They're represented differently. They're horizontal rather than vertical. They can be used on parts of a line as well as whole lines, and they work in both directions. Okay, let's work out some examples. So here's a proof. We have 3 premises and the conclusion is not R. Now if you look at this, R only shows up in one place, here. I could get R if I had this antecedent. I could do modus ponens to get R if I had this. How can I get not A, then E and D? Well, I know not A is the same as A. I can get that with double negation. So how can I get if A, then E and D? Well, here's A, here's D and E, which is essentially E and D. I can just use commutation to switch those anytime I want. How can I get if A, then D and E? Well, look, this is a conditional. If I could turn this into a conditional, not C, then D and E, I could do hypothetical syllogism. If that was not C and that was not C, and this was a conditional, I could get if A, then D and E, then do the double negation to turn A into not A, do commutation to turn D and D into E and D, then I'm there. If you didn't follow what I said, you will in a minute, because now this is exactly what I'm going to step through. So the first thing I'm going to do is turn line 1 into a conditional. I'm going to do conditional exchange on line 1. I turn the wedge into a horseshoe, negate the first component. C becomes not C. Everything else stays the same. D and D, D and D. Now notice I have my hypothetical syllogism. I have 2 conditionals. This consequent is the same as that antecedent. So these common ones kind of drop out, and I get this antecedent, that consequent, if A, then D and E. And that's by 2-4 hypothetical syllogism. Now what I'm going to do is I'm going to sort of work on this with the replacement rules to turn it into this. Okay, first thing I'm going to do is that I don't want A, I want not A. So I can use double negation on the antecedent there to get not, then D and D. If not A, then D and D. Almost there. It's supposed to be E and D, not D and D. So I'm going to use commutation to change the order of those two. Now I've got this, and it's this antecedent here. So now I can do my modus ponens on lines 3 and 7 to get R. Now I'm not done yet because the conclusion is not R. And you're saying, well, I know, Rick, not R is the same thing as R. Well, you're right, it's the same thing. That's why we have this rule of double negation, which lets us swap them out. Okay, let's do one more example. So the conclusion is conditional. If not A, then not C. By the way, you should be able to, at this point, just look at this and say, well, if I did conditional proof, this would be pretty easy. If I assumed not A, how could I get not C? Well, if you assumed not A, then I could get B by disjunctive syllogism, not D by modus ponens, C by disjunctive syllogism, and then double negation not C. And then you'd have your conditional, if not A, then not C. But let's not use conditional proof right now. Let's do it another way. What I'm going to do is, first I'm going to turn line 1 into a conditional. So wedge becomes horseshoe, negate the first component. Okay. Then I'm going to do commutation, and you'll see why in a second. Basically, I can explain to you exactly why. What I want is, if not A, then not C. What I'm going to do is get a string of hypothetical syllogisms. If not A, then not D, because these will match. Then if not D, then C. Then I can do the hypothetical syllogisms to get if not A, then C, do double negation on C. If not A, then not C. But first I have to get the right conditionals. So the first I'm going to get if not A, then B. I'm going to swap C and D to D and C, and then do conditional exchange on that. Wedge becomes horseshoe, negate the first component. Now I can do my hypothetical syllogisms. Okay, so I have, first I'm going to do the 3 and 4. This consequent is the same as that antecedent, so I can cancel these out and get if not A, then not D. Now I have 2 more conditionals, not D and not D there. They cancel out, so to speak, and I can get if not A, then C. Not quite there, I need if not A, then not C. So I'm going to do double negation just on the consequent, and that's by 8 double negation. Okay, let's do yet one more example before moving on to the rest of the rules. So here, when you look at this by now, you should, when you see 2 conditionals and there's a match between a consequent and an antecedent, the idea of hypothetical syllogism should kind of pop into your head. Now, you don't necessarily have to do it, but at least pop into your head and take a look. If we did hypothetical syllogism here, we would have this antecedent and that consequent. Is that anything like this? Well, here, the antecedent would be if P, then Q. This is if not Q, then not P. You don't know this yet, but you'll see it now. It's possible using the replacement rules to manipulate this so that if P, then Q can turn into if not Q, then not P. And obviously, P and Q can be manipulated into Q and P by commutation. So that's what I'm going to do. I'm going to work on this to turn it into if not Q, then not P. Work on this to turn it into if Q and P, and then do the hypothetical syllogism. Now there's three components to what I'm doing here, right? There's the hypothetical syllogism, there's manipulating this, and manipulating that. I could do those three in any order. Okay, I could do the hypothetical syllogism first, then I'd have this conditional, this antecedent, that consequent. Then I could manipulate, turn this into that, then turn this into that. So I could do the hypothetical syllogism first. I could manipulate these things first and then do the hypothetical syllogism. Either way, it's up to me. The way I'm going to do it is actually first I'm going to manipulate if P then Q and turn that into if not Q then not P. How can I do that? Well, first I'm going to do conditional exchange on this conditional. Okay, everything else stays the same. Horseshoe K, horseshoe K. It's just this that I'm working on. I'm going to turn if P then Q into not P or Q. Horseshoe becomes a wedge, negate the first component. Now I'm going to use commutation to swap the order of the not P and the Q. I'm going to move Q here and not P there. Now when I do conditional exchange to turn it back into a conditional, wedge becomes horseshoe, that goes down, negate the first component. So what I've done is in 2 steps, well actually 3 steps, I've turned this into that, if not Q then not P. Now I'm going to do the hypothetical syllogism. Okay, this consequent matches that antecedent. So I can get a new conditional that has this antecedent and that consequent. If not Q, then not P, then P and Q. Now all I have to do is swap the order of P and Q to get Q and P by commutation on line 6. And I'm done with the proof. Okay, let's move on to the last 7 replacement rules, and then we'll do a few examples. De Morgan's. This is extremely useful. It's going to come up a lot, so get used to De Morgan's, do a lot of practice with De Morgan's. What this says is that I can turn a negated disjunction into a conjunction. What I have to do, though, when I do that, okay, is I have to turn the wedge into a dot, okay, because I'm turning a negated disjunction into a conjunction, so obviously the wedge becomes a dot. I get rid of the negation, the thing that's negating the disjunction, so this outer tilde disappears, and I negate both of the components. So phi becomes not phi, psi becomes not psi. Now it works the other way. If I have a conjunction, I can turn that into a negated disjunction. Okay, conjunction dot becomes a wedge. I have to negate the whole thing, so I put the whole thing in parentheses and negate it. And then I also negate both components. Phi, not phi becomes phi, not psi becomes psi. Same thing works if I change the disjunctions into conjunctions and vice versa. I can change a negated conjunction into a disjunction. Okay. Step 1, I remove the outer negation, so that disappears. Instead of a negated conjunction, it's a disjunction, so the dot becomes a wedge. And I negate both components. Phi becomes not phi, psi becomes not psi, and vice versa. I can change a disjunction into a negated conjunction. This will make a lot more sense when we see some examples. Biconditional exchange. This is the only rule we have that lets us directly work with biconditionals. And what this says is that if you have a biconditional, you can swap it out for a conjunction of the two conditionals. And what I mean by the two conditionals is the conditional going from left to right and right to left. If phi, then psi, and if psi, then phi. Okay, phi, then psi, and psi, then phi. And vice versa. If I have a conjunction of two conditionals, which have the same components, but they're just in opposite order, phi, then psi, psi, then phi, I can swap that out for the biconditional. Next up, contraposition. This rule says that if I have a conditional, I can swap the order of the consequent and antecedent if I negate both of them. So remember commutation, which works on conjunctions and disjunctions. You can just swap the order because conjunctions and disjunctions are order invariant. You can't do commutation on a conditional. I can't just swap the order of a conditional, move the component on the left to the right and vice versa. But you can if you negate both of them. So this is kind of like commutation for conditionals. If it's a conditional, you have to negate both of the components. Now also remember, we did a proof, the last proof we did involved us turning this into that. So if we go back up here, you recall one of the things I did is I turned if P then Q into if not Q then not P. And it took it took 3 steps. Now we have a rule that would let us do that directly. If I were going to do the same proof now, I could immediately go from line 1 to line 5, and that would be line 1. The justification here would just be line 1 contraposition. Okay. By the way, another thing this means is that, strictly speaking, we don't need this rule. The work that this rule does, we could do with the rules we already have. It'll just take more steps. Instead of doing it in 1, which we can do now with this rule, it would take 3 steps every time we wanted to do this manipulation. So we don't really need contraposition. Distribution. This one's a little tricky to describe verbally, so I'm not really going to try and do it. Well, maybe I'll do it a little bit. If I have a conjunction, and one of the conjuncts is a disjunction, I can change that into a disjunction of conjunctions, where the first conjunct in each is the first conjunction out here. So this, another way of saying this is if I have phi and this disjunction, I can change that into phi and psi or phi and chi. And it goes the other way. If I have a disjunction of conjunctions such that the first conjunct is the same, I have phi here and I have phi here, I can, so to speak, pull that common conjunct out by itself over here. And the same thing works if I just swap dots and wedges. If I have a conjunction of disjunctions, the first disjunct is the same, I can pull that common disjunct out, okay, and go the other direction. This is another one that just is more intuitive when you've done it a few times. Exportation. This one, it's hard to describe, but it's kind of, it's intuitive if you think about it. Suppose, let's just translate this into some random English thing. If I have a bomb, then if I light the fuse, then there will be an explosion. There's two antecedents here, right? If I have a bomb, then, now there's another antecedent. If I light the fuse, then there will be an explosion. What this rule says is I can sort of combine these two antecedents into a conjunction. Now it says, if I have a bomb and I light the fuse, then there will be an explosion. And I can go the other way. If I have a conditional whose antecedent is a conjunction, there's two conditions, I can sort of pull, I can export that first condition out by itself as a separate condition. So it's kind of intuitive, even if it's hard to describe. Association is a little easier to describe. This will work either on disjunctions or conjunctions. But basically it says if I have three disjuncts, now we always have to associate. I can't just have phi or psi or chi without parentheses. But what this rule says, because intuitively you know that truth functionally it doesn't matter. You don't need the parentheses there. If you understand what we've been doing so far, then intuitively you kind of see that. This rule kind of embodies that knowledge. It says, yeah, this, if you want to, you can sort of reassociate. Instead of the first two disjuncts, I can associate the last two together. Same thing with conjunctions. If I have three conjuncts and the first two are associated, I can just shift the parentheses over and instead associate the last two. And finally, duplication. If you have any statement, you can replace that with a disjunction where both disjuncts are that same statement. And ditto with conjunction. Now you can see here again, there's a lot of redundancy in these rules. So for instance, I could go from this to this by duplication. I could also use the rule of DI to go from this to this. I can go from this to this by duplication. I can also go from this to this by simplification. So there's redundancy in our rules. Well, anyway, now we've got all 10 replacement rules introduced. So let's work through some examples. By the way, just because I'm stuck on PowerPoint slides here, I put the conclusion up here. Normally your conclusion would be after your last premise, but this last premise is kind of long. So I put it up here. Technically not correct, but sometimes we have to make sacrifices for PowerPoint. Okay. Well, I'm looking at the conclusion and I'm seeing this and I think, you know, because I've done a lot of proofs, I know that I can turn this into this pretty quickly. And then maybe I'll be able to manipulate it to get the conclusion. So watch what I'm going to do here. I've got A. And I'm thinking, okay, I've got A. I know that if I can get not A, I'm going to get A or B by DI. And then if I do De Morgan's on this, look what happens. Bam. Which is that. How the hell did I do this? How did I get from A to this mess in 2 lines? Well, the move from 1 to 3, that shouldn't be the issue, right? I went from A to A or B, which is using disjunction introduction. That's easy. How did I go from this to that? Well, that's De Morgan's. Remember, De Morgan's will let you turn a disjunction into a negated conjunction. Let me just remind you of the rule here. What I'm doing here, the move from 3 to 4 is moving from this to this. I'm turning a disjunction, which is what I have on line 3, into a negated conjunction, which is what I have on line 4, a negated conjunction. And what the rule says is I have to do 3 things. First, I have to negate the whole mess. So I've got this, I'm going to put parentheses around the whole thing and negate it, which is what I did here. Put parentheses around the whole thing and negated it. Second, I have to turn the wedge into a dot, which I did. Wedge becomes a dot. And the next thing I have to do is negate both components. Not phi becomes phi, not psi becomes psi. I'm going to negate both components here. This time I'm negating by adding a tilde. A becomes not A, B becomes not B. So the only tricky thing, the reason you might wonder why this is the same as that is because here the negation of the components involved removing a tilde, and here I'm adding a tilde. But remember, I can negate components by either adding or subtracting. So now I've got this, which is the antecedent of that. Footnote here for you. How on earth did I know to do this? Well, the only reason I knew to do this is because I've done a lot of proofs. And once you do a whole lot of proofs, you realize that if you have a statement, I can turn this into a negated conjunction that has this statement as the negation of this statement as one of the two negated conjuncts. You just do that a lot and you see that you can do it. Okay, so I'm looking at this and I saw that. So, oh, I can turn this into that in 2 steps because I've done it 100 times before. You just sort of see it there. Well, now the problem is that how can I get this consequent on the end here? I've got the antecedent. How can I get the consequent? Well, a couple of things to notice. Basically, it's hard to do. If I just use DI, if I just put wedge, not P here, well, then you might think, okay, I can do that and then do conditional exchange, but if I do conditional exchange, this tilde goes away. But I need that tilde there. So I'm thinking now, okay, maybe that was a dead end. And in fact, it was a dead end. I just wanted to do this to illustrate that sometimes you might have an idea about how to proceed in a proof, and maybe that idea doesn't work out. And that's completely a-okay. Then you can try something else. By the way, you could get this to work. We could do a conditional exchange, or I'm sorry, conditional proof on this, but I'm not gonna follow up on that. What I'm going to do instead is try something completely different. I'm going to look up here and say, if I do contraposition on line 2, this would move to the left, this would move to the right, both would get negated, so there would end up being a tilde here, and all of a sudden that would be the same as this. When this moves over and is negated, this tilde comes off. I'd have if P, then not P. So it would look like this. I'm doing contraposition on 2. This moves to the left and gets negated. This moves to the right and gets negated. Okay, in this case, it got negated by taking this tilde off of the antecedent. This got negated by adding a tilde. Well, now this is now I'm pretty close here. That antecedent is the same, and it's a conditional. Is there a way I can turn this into not P? That's what I need to do at this point, and I can. How do I know this? Again, because I've done a lot of proofs and I've done this basic manipulation 100 times in the past. I know that what I have to do is what I'm going to show you. First, I'm going to do conditional exchange. Horseshoe becomes a wedge, negate the first component. Everything else stays the same. And now, notice I have a disjunction, and both disjuncts are the same. So by the rule of duplication, I can just replace this with not P. And now the proof is done. Bang. Okay, let's do one more example. Now, if you look at this for a minute, if you've been doing a lot of proofs, you follow what's been going on so far fairly well, you should be able to see that this proof is valid just by looking at it and see why it's valid. It's valid basically because of hypothetical syllogism. Okay? The conclusion is if D, then C. Now, this consequent isn't the same as that antecedent, so we can't just use hypothetical syllogism to go if D, then C by HS here. But I want to point something out. Let's look at premise 1, which I've got here. If this is true, then clearly that is true, right? If this were an inference rule, this would be truth-preserving. Okay, how do you know that? Well, let's translate this into English and you'll be able to see why. Suppose I is I win lotto and S is I win super lotto. Okay? And so what this might say is if I win lotto or I win super lotto, then I move to Cancun. Okay? Well, clearly if that's true, if either me winning lotto or me winning super lotto will result in me moving to Cancun, then clearly me winning lotto will get me into Cancun. Okay?
Here's Cancun.
Also, notice that the move from here to here is also truth preserving. Okay? Suppose this means, what could this mean? I think I'm going to have to, we'll say, if I get a dog, then there will be poop in the yard and I will be happy. Let's say I like dogs. Okay, so if I get a dog, then both of these things, poop in the yard and I'll be happy. Well, clearly if that's true, then if I get a dog, I will be happy, because that was just one of the two things I knew was going to happen anyway. So both of these are truth preserving, and obviously if I had this, I could do hypothetical syllogism, because this consequent is the same as that antecedent, so I could do HS. You can see that truth functionally, I should be able to go from if D to C right here. Okay, truth functionally, because if D is true, then P and I are true. So I is true. And if I is true, then of course I or S is going to be true, therefore C. The problem is we don't have those rules. There's no rule that lets me do hypothetical syllogism where there's a mismatch. And we don't have a rule that lets us turn this into that or this into that. So here's how I'm going to approach the proof. I'm going to use the replacement rules to extract this from that and extract this from that. And then once I get these two lines on my proof, I can do hypothetical syllogism. So that's what I'm going to do in this proof. First up, I'm going to work on the second premise. So I'm going to try to turn this into D then I. First thing I'm going to do is conditional exchange. Horseshoe becomes a wedge, negate the first component. Now I'm going to do distribution. Now let me remind you of the rule here. What I'm doing is I'm basically moving from this to this. Okay? Here I have a disjunction whose second disjunct is a conjunction. So that's this. I have a disjunction whose second disjunct is a conjunction. And what I'm doing is I'm turning that into a conjunction of disjunctions. A conjunction of disjunctions. Okay? And the way that works is that my first disjunct here becomes the first disjunct in both of these. So not D becomes the first disjunct here, not D and not D. The second disjunct in each case is just these two in order. Not psi goes here, chi goes there. So P goes there and I goes here. So that's just distribution. Okay, moving from this to this. Now remember, what I want to get is if D then I. So I'm going to simplify the component off that has D and I in it. And then I'm going to turn that into the conditional. When you conditional exchange, wedge becomes horseshoe, negate first component. So now I have if D then I. So I'm halfway there. Okay, I turned this into that by manipulating it with the replacement rules. Now, remember, the second thing I want to do is I want to get if I, then C. Okay, so I'm going to use the replacement rules to get if I, then C out of this. First thing I'm going to do is contraposition. I'm going to move the consequent to the beginning, antecedent to the end. If I do that, I have to negate both of them. So C becomes not C, I or S becomes not I or S. Next, I'm going to, well, just to show you where I'm going, I'm going to do another distribution. But in order to do the distribution, I have to turn this into a disjunction where the second disjunct is a conjunction. Okay, right now this isn't a disjunction, and this component is not a conjunction. It's a negated disjunction. So I'm going to have to do a conditional exchange into Morgan's. So conditional exchange, horseshoe becomes a wedge, negate the first component. Now remember, De Morgan's lets me turn a negated disjunction into a conjunction. Okay, negated disjunction becomes a conjunction. Wedge becomes dot, both components get negated, I becomes not I, S becomes not S, and then I negate the entire thing. This whole disjunction falls off, and all I'm left with is the conjunction. Now I can do the distribution. Okay, just like here where I had a disjunction, second disjunct was a conjunction, same thing here. I have a disjunction, second disjunct is a conjunction. So I do my distribution. Remember, what I'm trying to get is if I, then C. So I want the component that has the I and the C in it, so I'm going to simplify the first one off. I want if I, then C, so I'm going to commute so I get the I on the left-hand side, then do the conditional exchange, if I, then C. Now, I've got my two conditionals. If D, then I. If I, then C, that consequent is the same as that antecedent. So by hypothetical syllogism, I can get if D, then C. And that's by 613 hypothetical syllogism. And that is the last example. So that is it. Next up will be section 4.5.